Good morning, students. Welcome to video lecturing class on dynamics of machines. So we'll continue with the fifth model, that is forced vibration, that the vibration measuring instruments. So we'll continue with the problems on vibration measuring instruments. So the statement is an undamped vibration pickup has a natural frequency of 1 CPS, that is cycles per second. It is used to measure a harmonic vibration of 4 CPS. If the amplitude indicated by the pickup is 0.125 centimeter, what is the correct amplitude? So here first we'll list the given data. He has given undamped natural frequency, that is Fn as 1 CPS, forced frequency as 4 CPS, and measured amplitude, that is Z, is 0.125 centimeter. So he has asked us to determine the actual amplitude. Okay. So for that we have the formulae Z by B equal to omega by omega n whole square divided by root of 1 minus omega by omega n square whole square plus 2 zeta omega by omega n whole square. So in this, in place of omega by omega n, we can substitute it as R. Okay. So now first you need to calculate the frequency ratio, that is omega by omega n. You know omega is given as 4 CPS and omega n is given as 1 CPS. So with the help of that you will get the R value as 4. So and in that equation Z is given, it has 0.125 centimeter. Okay, so he has not given any information about the damping, because in the statement itself he said that it is undamped vibration. So we can substitute all the values. Only unknown is going to be in that equation is B, that is going to be the actual value of the amplitude. So to substitute that, we will get the amplitude as 0.112 centimeter. Similarly, the next problem statement, a seismic instrument has a natural frequency of 6 Hz. What is the lowest frequency beyond which the amplitudes can be measured within 2% of error? Neglect damping. Again, it is an undamped system. So in this, the given data is 6 Hz, Fn is 6 Hz, and the error is 2%. Okay. So Z by B, if you take that ratio, that measuring value should be it is having 2% of the error. So therefore, if Z by B equal to 1, then the instrument is giving 100% correct result. But here he has given that it can give you the 2% of the error. So that means Z by B will be 1 plus 2% of that, that is 0.02, which will give you Z by B as 1.02. And zeta is 0 here. So we have the equation for Z by B. Okay. So in this, you know Z by B as 1.02. Omega n he has given in terms of hertz. Only unknown is going to be omega here. So solve for R this equation. Okay. So again here also you can take plus or minus. So that time you will get the range. Okay. So R is once, if you take 1 minus R square in that equation, you will get R as 0.716. If you take the denominator as R square minus 1, you will get the R value as 7.14143. Okay. From this, the higher the frequency ratio, lower is the frequency beyond which the amplitude can be measured within 2%. So we will take the higher frequency ratio, because it will give you the to lower the frequency, because it will give you the amplitude can be measured within 2% of the error. If you take the lower frequency ratio, that time the error may be higher. Okay. So from that you will get the F value as 42.83 Hertz. Similarly, the third problem, a commercial type of vibration pickup has a natural frequency of 6 Hz and a damping factor of 0.65. What is the lowest frequency beyond which the amplitude can be measured within 1% of error? So again, here also he has given natural frequency Fn as 6 Hz, and he has given the damping factor, that is zeta, as 0.65, and the error is 1% here. So that means we need to calculate F value, that is omega value. So z by b will be, as I explained in the previous problem, it will be 1 plus 1% of the error. So it is z by b is 1.01. So we have the equation for z by b in terms of r it is. Okay. So here we cannot neglect this term because he has given the zeta value as 0.65. Substitute that in this entire equation, only r is going to be unknown. Now you have to solve this equation to get the value of r here. So here you are getting fourth order equation. For fourth order equation, you know how to write the root. Okay, it is minus b plus or minus root of that equation you have to use to get the roots for this equation. Otherwise, from the calci directly you can get the roots for this equation. Okay, so x value you are getting it as 11.1979 and one more is 4.532. But x is nothing but here r square. We are replaced with this in this equation x by r square. So r will be 3.346 and 2.129. So selecting the higher value because it will give you the exact percentage of error. So we'll take r as 3.346. So r will be omega by omega n, that is f by fn. So in that, you know, fn value is given as 6 hertz. So if you substitute that, you will get f value as 20.08 hertz. Then moving further, a vibrometer gives a reading of relative displacement 0.5 mm. The natural frequency of vibration is 600 rpm and the machine runs at 200 rpm. Determine the magnitude of displacement, velocity, acceleration of the vibrating machine part. So here he has given that the reading of the relative displacement means it is a measured value z is 0.5 mm and he has given natural frequency as 600 rpm and force frequency as 200 rpm, and he asked us to calculate the actual value of the displacement, velocity and acceleration. So from the given data you can calculate the omega n by using this formula 2 pi nn by 60. So we will get it as 62.83 radian per second. Similarly, force frequency omega will be 20.94 radian per second. So the frequency ratio from these two will get it as 0.33. Now use this equation, that is z by b equation. So in this equation, you know r value, zeta you know. Okay, so in this equation he has not, again this also he has not given any information about the damping factor, so you can eliminate this term. So only consider this. So it will be r square divided by 1 minus r square. So r is already calculated and z is given, so only unknown is going to be b. So the displacement will be 4 mm and velocity will be x dot equal to omega into b, which seen while deriving the equations. So amplitude of velocity will be omega into b. So omega is 20.94. So we'll get it as 83.76 mm per second. Similarly, acceleration will be omega square into b. So we'll get it as 1753.93 mm per second. Then the next problem, a vibrometer having a natural frequency of 4 radian per second and the damping factor zeta is 2 is attached to a structure that performs the harmonic motion. If the difference between the maximum and minimum recorded value is 8 mm, find the amplitude of motion of the vibrating structure when its frequency is 40 radian per second. So here the given data are omega n is 4 radian per second, zeta is 0.2. And the difference between the maximum and minimum recorded value is 8 mm. That means this distance value he has given, but the z will be only this one from the mean line. So z will be 8 by 2, that is 4 mm. It is the amplitude value, and omega he has given the forcing function, he has given it as 40 radian per second. So then what will be the actual amplitude of the vibration? So for that You can use this equation, Z by B equation. So here you cannot ignore this 2 zeta term because zeta value he has given. So if you use that, and R can be calculated by omega n. You know omega value, omega n is known, R will be 10. So substitute in this equation. In this entire equation, only unknown is B. Okay. So from that you will get the value of B as 3.96 mm. 3.9632 mm. Okay. So here, whatever the problems we have solved in this video are on the vibration measuring instrument. Okay. So in this fifth module, we studied about the basics of the force function, force vibration, and the undamped forced single degree of freedom system. We derived the equation for the amplitude and phase angle, and a damped forced single degree of freedom system. Okay. Then we have studied about the magnification factor. Then we have studied about the base excitation. There are two parts. Then we have studied about the concept of the frequency response. So that we have studied about the vibration measuring instruments, and then critical speed, derivation of the critical speed equation. Then we solved the problems on magnification factor, and we solved the problems on transmissibility ratio, and we solved the problems on vibration measuring instruments. So in this module, you try to remember all the formulas which are related to the transmissibility ratio and the amplitude of vibration, and for the rotating and for the reciprocating, the amplitude equation will change there. Whenever there is a term eccentricity comes in the statement, you have to take that system is a reciprocating system. Similarly, you try to remember the equation for this vibration measuring instrument, that is Z by B equation, and the critical speed equation. Okay. So with this we'll conclude the fifth module, that is forced vibration. So try to practice the derivations and try to practice the problems and try to remember the formulas to solve the problems. So if you have any doubt, you can leave the comment in the comment box. Thank you.